This is the video for graphing rational functions, and the page that you're looking at, I've already taken the liberty of filling in all your transformations for your rational function. Your A value, that's essentially your vertical stretches and compressions along with the reflection of the x-axis. Adding a value or subtracting a value on the end of your function, that's your shift up or down. And then you have adding or subtracting a value from x in your denominator, which is a shift to the left or right. That's kind of like adding or subtracting a number inside parentheses or inside of a square root or something like that. So if you want to copy these down, you can hit pause, and then we're going to move on to some more of the other examples. All right, so these are just some terms and vocabulary that we're going to be using, and I'll talk about each of these individually, the zeros and the vertical asymptotes, as well as in-behavior asymptotes. Now, in-behavior asymptotes, this is a general category of types of asymptotes. Specifically, what we will be using in Algebra 2 are going to be horizontal asymptotes. These are just one of your in-behavior asymptotes. In pre-cal, you will also talk about slant asymptotes, which is a type of in-behavior asymptote. You can also have quadratic asymptotes and cubic asymptotes and all kinds of different asymptotes. So the ones that we are only going to be talking about, though, in Algebra 2 are going to be the horizontal asymptotes. And these are the ways that we can get those. Looking at the degree of the numerator and the degree of the denominator. Now remember that the degree of a polynomial is the value of the largest exponent. And so if the degree of the top is less than the degree of the bottom, then y equals 0 is going to be your horizontal or in-behavior asymptote. And then if the degree of the top is equal to the degree of the bottom, then your horizontal asymptote is going to be y equals the leading term of the top over the leading term of the bottom. And I'll explain these in more detail as we get to the examples. And then if the degree of the top is greater than the degree of the bottom, then there is no horizontal asymptote. This will create either a slant asymptote or a quadratic asymptote or whatever it may be. And again, that's going to be a topic for later on in your math career. We're also going to have things called removable discontinuities. These will show up as holes or open circles on your graphs. These will be, as the name implies, a discontinuity in the graph, which means that value is not actually a number that can be used in that equation. All right, so let's take a look at an example here. All right, so on this, this is our rational function. The first thing that you want to do with all of your rational functions is factor everything that is possible to factor. So the numerator we have is x minus 5. That cannot be factored. Can't do anything with that. The denominator, x squared minus x minus 12, can be factored down to this right here. So one of the things that we're going to be finding is going to be your zeros. Now your zeros, if you think about graphically, zeros are your x-intercepts. And on an x-intercept, that means your y value is 0. So that means this value right here has to be 0. Well, if you have a fraction, and if you take the numerator and divide it by the denominator, and you have to get 0 for an answer, that means your numerator has to be 0, because 0 divided by anything will give you 0. Doesn't really matter what the denominator is, as long as you have 0 divided by some real number here. All right, so what is the x value that will make this numerator equal to 0? that would be 5. So 5 is your 0. Simply mean that is where your graph intersects the x-axis, right here. Okay, so right there is your 0. All right, now let me take this off and let's look at some other things here. Vertical asymptotes. Vertical asymptotes are places where your function is undefined. Now, a function or a fraction is undefined when your denominator is 0. So look at your factors. What value of x would make each factor 0? Well, the value of x that makes this 0 is 4, and the value of x that makes this 0 is -3. Well, that means these two numbers right here would cause us to have a 0 for your denominator. Well, that would be an undefined function, which means that is where you will have vertical asymptotes. So that shows up right here. Now, your vertical asymptotes and horizontal asymptotes, for that matter, you need to draw as dotted lines on your graphs. Okay. All right. So then we have our end behavior asymptote. Again, we are looking at the degree of the polynomial. The degree of the numerator is 1. That's the largest exponent on the variable. The degree of the denominator is 2. Since the degree of the numerator is less than the degree of the denominator, that means y equals 0 is your horizontal asymptote. All right, so the x-axis is our horizontal asymptote. Now, you'll notice that we also have a 0 right here. So what actually is happening at this point is this right here. Our graph is coming above and it's crossing right there at 5, but then it's coming back towards the x-axis. All right, so yes, we do have a horizontal asymptote, and that's why I really prefer calling it an end behavior asymptote, because that's what is happening towards the end of the graph. It is asymptotic. It is not going to cross the x-axis again. Your graphs can cross the x-axis locally in this area, but your end behavior asymptote means what is happening as your graph goes forever to the right or forever to the left. Is the x-axis asymptotic? Yes, it is. Over here, your graph is approaching the x-axis from below. Over here, your graph is approaching the x-axis from above the x-axis. So we do have those two things. One of the other things I do not have listed on here is going to be a y-intercept. Now remember that for a y-intercept, your x values are 0. So if I want to know the y-intercept for this function right here, all you have to do is put 0 in for x. Well, if you put 0 in for x, this term goes away, that term goes away, and that term goes away because they would all be 0. So that means you have -5 over -12, which would be 5/12. That is your y-intercept. That's just a little bit less than a half, and you can see on your graph that's where it crosses the y-axis is just a little bit less than a half right here. Okay. All right, so let's now the one thing that we didn't have on that problem was a removable discontinuity. So if you look at this example, I'm not going to go through the whole thing, but a removable discontinuity, you get that whenever you have a factor from the numerator that cancels with a factor from your denominator. The value of x that makes that factor 0 that is where your removable discontinuity will occur. So in this case, -2 would make this factor equal to 0. So x equals -2 is your removable discontinuity. Now, your removable discontinuity is really a point. It's this hole right here. And so what we need is a coordinate for that point. Well, to find the y value for that coordinate, what we need to do then is take this -2 and plug it back into the reduced fraction here. Now the reduced fraction is 1 over x plus 4. So if I plug -2 back in right here, that's going to give us 1 over 2 for the y value. And so you can see at -2 comma 1/2, that is where we have this open circle, which is called a hole, or the mathematical term is the removable discontinuity. All right, so let's attack a few problems here and see how these work out. First step, we do need to factor everything that can be factored. Now the numerator cannot be factored. The denominator can be, and that goes down to x plus 2 times x minus 2. That's a difference of 2 squares. The zeros we get from the numerator, and so the x value that makes the numerator 0 is 3. It means our graph is going to cross the x-axis at 3. The y-intercept is when your x value is 0. And if we put 0 in for x, that leaves us with -3 over -4, which is positive 3/4. All right, so positive 3/4 for the y-intercept. Your vertical asymptote is going to come from your denominator here, and that is the x values that make your denominator 0. Well, that would be a -2 and a positive 2. So plus or minus 2, those are your vertical asymptotes, so we graph those as dotted lines on here. The end behavior asymptote, you look at the degree of the numerator, which is 1, and the degree of the denominator, which is 2. The degree of the numerator is less than the degree of the denominator, meaning y equals 0 is your horizontal asymptote. Now I'm not going to try to draw a dotted line on top of the x-axis, but the x-axis will be the horizontal asymptote here. We do not have any factors that cancel, which means there is no removable discontinuity. So that does not apply to this particular problem. Now your domain. Your domain is going to be everywhere that your graph exists. So we're going to have some graph here. We're going to have something in between the asymptotes and have stuff after the asymptotes. So it's essentially everywhere except where the asymptotes are. So that means your domain would go from -infinity to -2, union -2 to +2, union +2 to positive infinity. All right, so just to sketch out the rest of the graph, the rest of the graph is going to look like this in this section. It's going to come down, and it's a little lopsided here. This part of the graph right here is not symmetrical. All right, it is intentionally a little bit lopsided here. And then over here, what our graph does is similar to what it did in the other problem, which is it crosses the x-axis, but then it comes back down towards the x-axis. So it is asymptotic as it approaches infinity out here. Okay. All right. Next problem. Factor everything. So the numerator factors to x plus 3 times x plus 2. The denominator factors to x plus 2 times x minus 1. Now what you'll notice here is that we're going to have a, change my color here, we're going to have a factor x plus 2 that cancels in the numerator and the denominator. What that does is it creates our removable discontinuity. So we will have a removable discontinuity at -2 for an x value. Now, to find the y coordinate, we'll take that -2 and substitute it into the terms that are left in our numerator and denominator. -2 plus 3, well, that's 1. -2 minus 1, that's -3. So -1/3 is the y value. So at -2, -1/3, we're going to have an open circle or a hole on our graph. All right, so now the zeros. The zeros we get from the numerator, and the x value that makes the numerator 0 is -3. All right, so graph crosses the x-axis right here. The y-intercept you get by putting 0 in for x. Well, that's going to just leave us with +6 over -2, which is -3. So -3 on the y-axis is the y-intercept. The vertical asymptote, well, we get that from our denominator. Now, -2 is not a vertical asymptote because that was part of the removable discontinuity. The vertical asymptote is only at x equals 1. So we will put our dotted line at x equals 1. The end behavior asymptote, we look at our degree. The degree of the numerator is 2, and the degree of the denominator is 2. So if you just took the leading terms, x squared over x squared, that reduces to 1. So y equals 1 is our end behavior asymptote. All right, so our domain goes from -infinity until we come to our first discontinuity, which is right here. So it's going to go to -2, union, and then our graph is going to go from -2 to the next discontinuity, which is 1, union, and then 1 to positive infinity. Now we can kind of see the curvature of the graph right here going through these 3 points, and that's going to give us our graph. It's kind of easy to see here, and then it has to approach the asymptotes, and it will do the same thing in the diagonal quadrant up here. All right, next problem. Now the only thing that we can factor out of this problem is going to be our denominator. All that we can really do is factor out a 2, which leaves us with x plus 3. Again, the 0, we get that from the numerator. The x value that makes the numerator 0 is -4. So our graph crosses the x-axis at -4. The y-intercept we get when x is 0. So that leaves us with 4 over 6, which reduces to 2/3, so 2/3 will be the y-intercept. It's just approximate. The vertical asymptote is the value that makes your denominator 0 here, which is -3, so that's going to be x equals. Remember, your asymptotes are lines, which means you need to write them as x equals or y equals. So x equals -3 is going to be our vertical asymptote. The end behavior asymptote, well, if you look at the degree of the numerator and the degree of the denominator, they are both 1. So if you take the leading terms, x over 2x, that reduces to 1/2. So y equals 1/2 is our horizontal asymptote here. All right, so we do not have any factors that cancel, so therefore there is no removable discontinuity, which means our domain is going to be from -infinity to the only discontinuity we have, which is at -3. That's our vertical asymptote. And then union -3 to infinity. And the sketch of the graph that we will have is going to approach the asymptotes on this side, and it'll look similar on the diagonal quadrant here. All right, so there's a sketch of our graph. All right, this is the last one we're going to go through here. And so factoring the numerator, the GCF of 3x can be taken out, leaving us with x plus 4. And then your denominator factors to x minus 3 times x plus 1. Once again, we do not have any factors that cancel, so there is no removable discontinuity. The zeros we get from our numerator. There are two values of x that will make our numerator 0. One of them is -4 right here. The other one is going to be 0, because 3 times 0 is 0, and then 0 times your parenthesis would also give you 0. So 0 and -4, those are the zeros. 1, 2, 3, 4. Y-intercept, well, if you put 0 in for x for the y-intercept, you're going to get 0 over -3, which is just 0. Vertical asymptote we get from the denominator, so x equals 3 would cause your denominator to be 0, and so would x equals -1. So -1 we have right here, and x equals 3 will be located over here. All right, so the end behavior asymptote, the degree of the numerator is 2, so is the denominator. If you take the leading terms, that reduces to y equals 3. So y equals 3 is our horizontal asymptote here. And the domain is going to go from -infinity to your first discontinuity, which is the vertical asymptote, -1, union, and then -1, to the next asymptote, which is 3, union, and then 3 to infinity. All right, so I just noticed I do have a little bit of a mistake here. Hopefully you caught that mistake. Up here, I wrote down a +4 when it should have been a -4. So let me take that out and change that to a minus. Now, what that changes is our 0 will change to a +4 right here. Changes the graph to a y-intercept of +4 over here. All right, and that's all that that mistake changed. So now to look at what the actual graph looks like. The actual graph of this function looks like this in the middle. It approaches the two asymptotes going through the origin. On the left side, it's going to approach the asymptote on the left and the right. And then on the right side, it goes like this. Now, remember that this is an end behavior asymptote, which means the graph can cross that asymptote locally, but it's what happens at the ends of our graph as we go to infinity and positive and negative infinity that matters. So as our graph goes to positive infinity, this graph does approach that asymptote. And as you go to negative infinity, the graph approaches that asymptote as well. This one from the top, this one approaches it from the bottom, but it's still an asymptote. All right, that is going to wrap up several examples on rational function graphing and the transformations.